Okay, I think I can start now. So thank you everybody for coming. In the next minutes, I will give you a quick overview of the basic ideas at the roots of my work. And before starting, I want to introduce my paranames, Marco, Ph.D. here at the University of Twente, and Mattia, who came from Spain, so you can be seated. So I will start my presentation explaining one of the most important terms that will be recurrent through all the work, which is excited states. So as you probably know, a molecule usually is found in nature with some distribution of its electrons, which is the lowest possible energy for this kind of molecule. But alongside these electronic distributions, many other are possible, which anyway will produce a higher energy for this molecule. And if we provide to our system a correct amount of energy, we can make so that the molecule makes a transition from the ground state to an excited state. So the important thing to remember is that in excited states, molecule, thanks to this different electronic distribution, have very different physical and chemical properties with respect to the ground state. Once a molecule is in its excited state, many things can happen. For instance, they can undergo to a geometrical reorganization, so stretching or compression of the bonds or changing the angles between their molecular bonds in order to minimize the energy of the molecule still staying on the excited state. So basically we go from this point to this point on the excited state. Or they can jump to other excited states, or again, they can release the energy that they gained, they came back to the excited state, to the ground state, sorry. So in the work, I mostly focus on the process of absorption and on the process of geometrical relaxation. One source of energy that we can give to the system to induce this ground to excited state transition is light, because indeed, as you already know, light, white light that is around us can actually be decomposed in different colors corresponding to different wavelengths, which are associated to different energy through this equation. So there is an inverse proportionality between wavelength and energy, and this means that the colors that are at the left of the scale have higher energy than the colors that are at the right. And if we look at the constant of proportionality between these quantities, we see that it is the product of speed of light, c, and the Planck constant h, which tells that there is some quantum mechanics involved in all these light absorption and electronic transitions. But after all, we don't have to think that light absorption is something weird or abstract, because it actually happens every moment around us. For instance, in the plants, the process of photosynthesis is started when a chlorophyll molecule is excited, or also in our eyes when the retinal chromophore absorbs light and initiated the process of vision. I said chromophore, and this is another important term to remember, because with this name we call the photoactive molecule that is responsible for the light absorption in a system. These two examples are examples of very complex chemical and biochemical events, but only one single molecule is responsible for the light absorption and undergo to an electronic excitation. So giving a closer look to what means electronic excitation, we can have here a simplified picture, a very schematic thing, and just to give a flavor of what happens. So I said that a molecule in its ground state has an electronic distribution that minimizes its energy. And one possibility is to distribute all the electrons that in this scheme are the black dots. And we can distribute them on the molecular orbitals so that they are paired. Each molecular orbital is basically doubly occupied. This is the easiest thing that we can do to minimize the one energy or to approximate this. And according to the fundamental rules of quantum mechanics, we cannot just put all the electrons in the molecular orbital which has the lowest energy. The term molecular orbitals identifies three-dimensional functions that tells us the properties of certain electrons, and they can be seen like steps in an energetic ladder. So we will have some of them describing electrons very low in energy till one that describes the highest occupied molecular orbital. So when we give light to our molecule, one electron, what happens is that one electron can jump to the lowest unoccupied molecular orbital, giving the electronic distribution typical of an excited state, something like this. And an important requirement is that the difference between the energies of the states must be equal to the energy of the incoming photon. And if you want to give a look to these molecular orbitals, we can easily plot them. So they are just three-dimensional functions, basically. So we have an electron that jumps from the oxygen of this molecule, the red dot, to a function that is more delocalized on the chain. But then the question is how to compute these energies. We have to resort to quantum mechanics. Basically, we want to solve the Schrödinger equation, this equation, which has this complicated term, which is called the Hamiltonian operator. And basically, all the story is complicated by the presence of this term, which attests the instantaneous electron-electron repulsive interaction. But this is a powerful equation. We can compute many things. For instance, we can compute the structure of the atoms, computing so the electronic shells, but we can do much more. And to do much more, we need powerful computers, and we need to tailor some good approximations to solve this complicated equation. Indeed, solving the Schrödinger equation is a computational effort of increasing requirements. For a simple case, such as a hydrogen atom, if we are good enough, we can also think to sit down and be patient for about 1 hour, and we can get to an analytic solution. This is definitely not possible anymore, even for a small system. In this case, we surely need a computer with some quantum chemistry code, which can anyway do the job quite efficiently. But the problems increase when we go to even bigger systems, so more interactions, more molecules, more stuff to compute, and we need to resort maybe to cluster of computers, so the problems are just bigger. But once we solve the Schrödinger equation, we can just not compute energy differences. We can also compute the forces acting on a molecule. We can see this in an approximation, considering a molecule as like a set of classical spheres connected by classical springs. The equation telling us the force acting on a classical spring is this one. So if we want to find the equilibrium distance of the spring, so x naught, we just put this term equal to 0 and we solve for x naught. An example is a molecule of H2, so two classical spheres connected by a spring, and we can see that the energy profile is this one. So we have a region where the two atoms are too close to each other, one region where the two atoms are too far between each other, so they basically break the bond, and one region where the optimal geometry gives the minimum of the energy. The complication arises when we want to study these in excited states or also in complex environments. Why it is important to worry about complex environments? Because basically light absorption happens in protein or solutions, and the environment affects in a big manner the absorption properties of the system. For instance, retinal absorbs when it is isolated in the green part of the spectrum and in the blue part when it is embedded in its protein environment. So how can we proceed? A first idea could be, I don't care, I just take everything and put it into the Schrödinger equation, eventually we'll solve it, but it's not really a smart thing to do because all this game is just too expensive from the computational point of view. So we have to play it smarter, and the smart approach is to identify a region of the system which is really responsible for the ground to excited state transition. We will treat this quantistically, and the rest of the environment can be seen like a spectator, so something that influences the chromophore externally, and we can treat it at the cheaper level of theory, such as classical molecular mechanics. There are many possible combinations of quantum in classical, and basically the things that one has to wonder are these questions. So since we cannot make an extended quantum treatment, we want to do a quantum in classical, so we have to wonder how complex should this partition be. So how we make the coupling of the classical equations with the quantum equations, and in this way, which effects are we actually including? And most of all, if we are missing something important that is indeed present in the physical phenomenon under analysis, but we are not recovering. So the final solution is, of course, as everything, finding a correct balance between the quantum part and the classical part. The quantum is very specific. It gives us a lot of information about the system, but it is computationally quite demanding. On the other hand, the classical approach is cheap, is general, but sometimes it is too simplified, so we miss some physics in our problem. And we want to find a correct balance in all this. So this is all. I hope I gave you a flavor of what I've done. The ceremony, well, the defense will start now. And yeah, that's all. Thank you for listening.
I open this public meeting of the doctorate board of the University of Twente. I welcome you all, in particular the relatives and friends of the candidate, and a special welcome also to the external members in our committee, Dr. Ensing from the University of Amsterdam, Professor Groenenboom from the University of Nijmegen, and having traveled the farthest, Professor Amovilli from the University of Pisa. Welcome. And a welcome also to our internal members, Professor Briels, Dr. Brox, and of course the promoter, Professor Filippi. Dear candidate and the paronyms, may I ask you to take your position here on the podium. Okay, Professor Amovilli, I invite you to start the opposition.
Okay. Dear candidate, I read your dissertation and I found it well written, well detailed, and also with an exhaustive bibliography. After this reading, I have some questions for you. Let us start with DFT.
Yes.
You use DFT and time-dependent DFT to perform calculation on excited states. But we know that there is a plethora of functionals. And which are your guidelines for the choice of a good or at least a reliable functional for your purposes?
My highly learned opponent, thank you for your nice words and thank you for your question. So, generally answering, we know that time-dependent DFT can have some shortcomings in situations when it has to describe excited states with a strong character of charge transfer, for instance, or with very delocalized densities. But on the other hand, it is also a very powerful tool for computation, such as minimization of energies in ground and excited states, or even it is widely used for computing vertical excitations. So the guidelines that I followed was basically to find a functional that was immune of some well-known shortcomings. For instance, to compute excitation energies, we mostly employed Cambit-Relip, which is known to solve the problems related to spurious excited states, which are usually found at a lower energy with respect to one excited state that one aims to analyze. For instance, I used Cambit-Relip in the study of the excited state of retinal in rhodopsin, and we find this functional to perform efficiently, since we've always found excited states very, very clean. So we were always able to identify the excited state of interest with the correct features. So in the case of retinal, we always saw a clear HOMO-LUMO excitation associated with a high value of the oscillator strength. So from the literature, we knew that this functional could perform properly.
So it belongs to the last generation.
Sorry?
It belongs to the last generation of
Yes.
functional.
Yes. So long range.
Non-local exchange,
Yes.
hybrid, and
Yes.
also.
For other studies that we performed, we made like a wide investigation of several families of functionals. For instance, in the study of geometry optimization, we investigated several different families, and we tried to find a connection between, for instance, the family of the functional and the quality of an excited state that we optimized. And in this case, we see that there is a wider spread of the results, and we didn't manage to find a direct link between the family of the functional and the quality of the excited state, estimating the quality with respect to a correlated approach.
Did you encounter a problem of static correlation?
Sorry?
Did you encounter problems of static correlation?
In in our study, I think we rarely meet problems of static correlation, because you mean using density functional theory.
Yeah.
Well, yeah, I can say that from the results that we found, in some cases, the density functional approach was lacking some correlation effects that instead were recovered with higher approaches like perturbation approaches or Monte Carlo.
Have you never used an approach based on unrestricted DFT? Let's say, for example, if you want to study the twisted geometry
Oh yes,
of the excited
well,
state of acrolein.
yes. In that case, we discarded the use of density functional theory because in this sense, yes. For instance, when I treat the excited state of acrolein in its twisted geometry, we have a breaking of a bond. So basically, the state must be described as a diradical. So it is an open shell, and since density functional theory is a single reference approach,
Yeah, but maybe unrestricted can be.
yes, it could have been.
I don't know what happened.
But we didn't.
Okay.
We didn't employ it.
Okay. So you used also, other than the FT, several methods based on the calculation of the wave function.
Yes.
CASCF, CASPT2, and so on. And which of them compares better with variational Monte Carlo, which is your standard in some
Yes.
sense of your thesis?
For in basically all the applications that I studied, Monte Carlo approaches have a good are well compatible with the perturbation results, and as long as we use, of course, compatible active space for the wave function, and as long as we use we recover the same physical effects in the reference wave function, the Monte Carlo method performs gives compatible results in the study of excitation energies and also in the calculation of geometry in the ground and excited states, which are compatible with the perturbation approaches.
So CASPT2 and
CASPT2,
FPT2.
yes, these are the two methods that I mostly use.
And QMMM is a way to attempt the study of complex systems like those that you mentioned in the title, biomolecules of increasing complexity. And the definition of the QM portion of the system is not well given, in the sense that one has to choose. And which are the limiting factor in the design of the QM system, the active system?
So, as you said, the partition of quantum and classical part is one of the crucial things in the approach of a QMMM calculation. And basically, when we create this partition, we have to take care to an aspect fundamental, which is where is localized the electronic transition. In the cases that I studied, the electronic excitation was always well localized on a single molecule. So the excitation was belonging to the orbitals of the chromophore only, and we never saw a spread of the density on other molecules of the environment. And this is basically one of the most important things to take into account. On the other hand, if I saw an excitation on the chromophore coupled with some excitation of the environment, or with a spread of the density on some amino acid for the case of retinal, or on some nearby water molecules in the case of explicit solvents that I treated, I should have included them also in the quantum region. So basically, to design a quantum region, I want to include all the molecules that have something to do with the excitation process.
If you add the solvent molecules to the QM system, there could be the problem of the flexibility, because the QM system becomes flexible in the sense that you have to consider also the orientation of the molecule that you add.
Yes.
No possibility of interaction with the environment.
Yes, indeed, including the more molecules we include in the quantum part, the more complication, as said, we have to take into account, of course. And yes, we should
This
also
is a limiting.
yes, it is a limit of the approach. And yeah, also for the sake, for instance, of the shape of the orbitals, we should design properly which orbitals to include in a wave function based method, for instance, which should also include orbitals of the environment, and this would increase the computational cost of our approach.
Which are the basic interactions between the QM and the environment that need to be considered for a reliable result?
So the interaction of QM with the MM part are, first of all, electrostatic effects. So those generated by an external field, a permanent external field, such as the one generated by point charges. And on top of this, we investigated, of course, the use of polarizable dipoles. So the transient interactions between a dipole and the density of the solute. So these belong to electrostatic family of interactions, and we found that using polarizable force fields, we can also simulate more complex kind of interactions, such as the ones generated by the transition dipole moment of the molecule, which interacts with the environment. So we call them resonant interactions. So these are basically the two main effects that we are including: electrostatic, either given by point charges or polarizable dipoles, and resonant interactions.
Now you are going to introduce also not classical interactions.
Yes, exactly.
Because they are important.
Yes, we in some cases we can find that including these non-classical, so resonant interactions, it is
and also dispersive interaction.
Yes, it is a key to have more reliable results.
Professor Amovilli, are you satisfied with the answers of the candidate?
Okay, yes.
Okay, thank you. Then I would like to ask Dr. Ensing to continue the opposition, please.
Thank you very much. Dear candidate, let me also first congratulate you with a beautiful piece of work. I really enjoyed reading it. You clearly did a lot of work and of nice quality, if not to say a very good quality. Still, I have a few questions, of course. And let me start by just a simple question about the method section. I understand that you actually did quite a bit of method development and coding yourself, and I was just wondering about the polarizable force fields. For example, what you describe on page 38 and 39 about the coupling between the polarizable force field and the electronic structure calculation. Did you implement that yourself as well?
My highly learned opponent, thank you for the nice words. And so we worked on the implementation of polarizable force field, and I took part in some part of the implementation. It was not implemented at 100% by myself. But yes, this approach was brought in the Monte Carlo code developed within our group, and we also used for time-dependent DFT an implementation that was done in the University of Pisa. But in that part, I didn't take any part.
Okay. Yes. So then my real question, I suppose, is about this part. So to do the polarizable force field, I mean, to find that structure, you should do that, I guess, in a self-consistent manner as well, right? And I can imagine two ways of doing it, or maybe three. But let's say you could just do the SCF, then optimize dipoles, do the SCF again, dipoles again. Or do you do this all self-consistently at each iteration in an SCF? You optimize also the dipoles.
Yes, these are actually two approaches. In some code, such as Molcas that we used, it is implemented in this way. So micro iteration of self-consistent. So we, for instance, in CAS SCF, I think it is done with micro iterations of the wave function and the electric field and the field of the dipoles. In the code chump that we used, we did it in the other way. So we optimized the dipoles externally after we brought to self-consistency the wave function. So to be more clear, what we developed.
But then, so in the second way, then you stop. So you do the SCF, then you do the dipoles, or you do a couple of iterations. So how many iterations?
We do iterations outside. So I'll be more clear. So we start from a given wave function. Let's say maybe a single state wave function, just to make it easier. We optimize this wave function in the presence, let's say, of some point charges. Yeah. Once we have optimized the wave function, we introduce the environment of the dipoles. Yeah. So in this moment, again, we need to reperform an optimization of the wave function, now in the presence of the dipoles. Yeah. After we perform this iteration, we need again to induce the dipoles on the new density of the quantum part, and we repeat this external. So I say external cycles because are external to the SCF itself. So we do the SCF in a certain field, we update the field, yeah. We update the SCF, and so on till we reach self-consistency. And we check this in chapter 5. I checked that self-consistency was reached checking the convergence of the energy gap between ground state and the excited state of interest. So when we see that this...
so how much more expensive is it to do the SCF in that way compared to a static force field?
Actually, we found that it is not, also this approach, it is not very expensive, because just in a couple of iterations of self-consistency.
Yeah. So factor of 2? Or?
Yes, something like that. So, yes.
Yeah, and you don't think the order of doing things, so either every cycle or this SCF, it will give you the same solution?
For what we checked, looking at the results, we found compatibility between these two different approaches. So I believe it doesn't really matter.
You don't get you never found that you got stuck with the wave function because you started with a strange.
No, we found instead that it is the approach is quite robust, because regardless the starting point of the wave function and the starting dipoles, we always end up in the same value of the energy. So yes, in this sense, it is quite stable as approach.
Very interesting. I have some questions about chapter 6, 5, and 6, especially about. Let me start with a question about this. The force field, the water force field, for example. So sometimes you use the Amber protocol, I think, charges of the tip 3p, which are something like minus 0.8 and plus 0.4 for the O and oxygen and the hydrogen or something. But sometimes you do it yourself again with MP2. So you calculate these rest charges at the MP2 level of theory. So you find some other numbers, minus 0.7 to 6. And can you explain briefly why you do that, and if you think it makes a difference?
Okay, so in this chapter we used we did let's say 2 steps partitioning of the system. We do QM, which is the retinal, plus the residue of lysine, which is covalently linked to it. So this is the part treated at the QM. We treat an environment in a radius of about 15 angstrom from the chromophore at the polarizable level, and all the rest with the just point charges, so static field. And we found that using the RESP charges, for instance, for the waters that are polarizable, produces a better quality of the results, since these charges are designed in order to also they have a lower value of the charges, so the magnitude of the charge is lowered, because then we will put a field of dipoles on it.
Sure. This I understand. But so the thing that worries me a little bit is that original charges are made in a sort of protocol, the Amber protocol,
Yes.
or whatever force field you take, to be sort of consistent with then the Lennard-Jones, the van der Waals parameters, let's say, so that well, there may be electrostatic attraction, but then you need also repulsion, of course. And so, if you would change one part of the force field, wouldn't you need to also change the other part?
I would say no, because I mean, according to this approach, we are consistent within each partition of our system. So, except possibly interactions between MM pole environment and MM, that maybe could introduce some bias. But I mean, at the moment, I think it's quite reliable as thing, because if I have to think about it, maybe I don't know. Maybe this interaction can be somehow biased, but I didn't investigate so far.
Am I allowed to ask another
If you
question?
have a short question,
Sure.
then
I would like to ask you a little bit about the sampling. You write, for example, that you do a long trajectory, a QM, MM, MD trajectory to sample
Yes.
structures from, and to make sure that you don't get stuck in some unlucky structure. Or now, I was just wondering, how long is a long QM, MM trajectory, and in particular, do you think you can actually capture motions and the configurational space of a protein in a membrane?
So the simulations were run for about 15 to 20 picoseconds, I would say.
Right.
So I think this has been a time of simulation sufficient to describe properly the configuration space of the protein.
But the motions of a protein are on a much longer time scale, don't you think? I mean, I don't know how you start exactly, but if you take a structure from an X-ray diffraction pattern, let's say, then well, you have to first relax, of course, the protein in water or in a membrane in this case, and the protein fluctuates on a long time scale. So, do you think you capture the typical states of the environment?
Well,
from such a
I would
trajectory?
say that I didn't perform myself the QMMM and the simulation, so I've not big experience on QMMM MD.
Okay.
So I sincerely, I believe that my co-authors did the best to describe properly the
Yes.
protein environment. I cannot answer clearly to your answer. I'm sorry.
Okay. Thank you very much.
good. Then we continue the opposition. Thank you very much, Dr. Ensing, with Professor Groenenboom. Please.
Thank you very much. Dear candidate, also like to congratulate you with this thesis where you describe, I would say, alternative methods to density functional theory, and I think that's a valuable contribution to the field, to the dominant paradigm maybe. I understand method development is the focus and you compare many different theoretical methods, but I would like to start a discussion by how your results should be compared to experiment, what sort of the ideal thing would be. And then specifically, I think about, you look at the effect of solvents on electronically excited state, but presumably you can use this to understand the spectrum where you absorb a photon and then in the excited state, maybe a molecule relaxes and at some point you have emission. But there are various things that can happen. Of course, electrons may respond sort of instantaneously in the excitation, but you discussed the reorientation of molecules, of the solvent molecules can happen. There is the geometry relaxation of the molecule, and then there is the time scale of emission. I mean, the photon can come out instantly, or so. Especially I think about chapter 5. What are sort of the time scales, and how should I go through this process and compare to experiment?
You said sorry. It's
yeah. So
About chapter 5?
I was thinking about the systems, the acronym and the
Yes.
MCP that you described in,
Yeah.
for example, in chapter 5.
So my highly learned opponent, first of all, thank you for the question. I have to say that for the sake of chapter 5, the comparison with the experiments was not our prime matter of concern. For this reason, we indeed used a very reduced model for a solvent, few molecules. In the case of acrolein, we even used a very asymmetric cluster. This was all done to allow us to have a super molecular system which we were still able to treat at the correlated level. Moreover, we are using a single point geometry, so it is a cluster geometry optimized within density functional theory. We didn't do any molecular dynamics on it. So I think that we didn't really think about a direct comparison with absorption in water to be compared with experiments. I think that approaching these kind of problems with polarizable force field is I think it can be done, but of course it will require more investigation, maybe definitely a complete novel implementation of the computational approach. So for what concerns the timescales, yes, it is true. In this work, we just assumed the Frank Condon principle, so direct response of the electrons with excitation, and the polarization effects just retrieve the instantaneous, so the fast response of the molecule of the environment. And
When
yes.
you say, sorry, can I interrupt you? When you say fast response of the molecule,
Yes.
You mean of the motion of the molecule?
No, no. I'm talking about electronic response.
Okay.
So in a frozen geometry, we just take into account the fast response of the
electrons.
Yes. So in the fast response of the environment is simulated through the use of the dipoles, which actually respond electrostatically to the excitation.
Can I for this ask also, because on page 87 you say we assume fast response of the solvent, but then you also say reorientation, right? Or did I misunderstand? That's on page 87.
Sorry.
If you look at page 87, where it says 4.2 methods, and the last for a few sentences, we assume a fast response of the solvent, namely that the solvent molecules have time to undergo the orientational reorganization induced by the structural changes of the solute in the excited state.
Yeah, I see. 1 second, I read the... So here we're talking about the PCM method.
Yes. Well, maybe I'm beginning to understand. So here you're saying that the solvent follows the molecule sort of instantaneously.
Yeah, so in this approach, we're not really concerned with the geometrical structure or the geometrical conformation and orientation of the solvent, since we have just a continuum medium. And okay, in this case, yes, the response in this case, it's related to the use of the electric constant. So in this chapter, we are doing a study of geometry minimization. So we are using the epsilon, which is different from the resonant epsilon. So in the PCM method, we use this static dielectric constant in the calculations because, yes, we want to simulate exactly a situation in which the molecule is excited, it survives in its excited state, and if it decays to its ground state. So we simulate this, describing the environment with the static dielectric constant. sorry, I misunderstood at the beginning, but yes, this justifies the use of the static electric constant. On the other hand, if we wanted to simulate or compute vertical excitations in PCM, we would have used the resonant value of the electric constant. So epsilon infinity is usually called, because we do not describe the slow degrees of freedom of the environment.
Okay, thank you. Now, is there time for question?
There is still time for a short question.
Okay,
if you like.
then a little bit different question. At some point, you sort of optimize your bases, right? You look at hydrogen, your oxygen, you do the double and the triple zeta, and you have your prime basis,
Yes.
and you tweak them. When you test these things, you describe the effect on energy. You say, okay, the energy effect is small. And at some other point in your thesis, where you compare different active spaces in the KCCF, and you look what do these things do on geometries. I would expect that it would be very important here when you make these changes, study a basis set, active space, compare methods, to look at the values of properties like the dipole moment of the molecule, the dipole moment of your solvent, or the polarizability of the molecule, and see how these properties change when you use different basis sets or different active spaces, because I would assume that is very important on the effect of the solvent. So why don't I see tables with dipole moments? That's my simple question.
So in the cases of geometry optimizations, we always took care double checking that the excited state that we were optimizing was actually the one with the correct physical properties. So for what I saw in the molecules treated, features such as transition dipole moment are very stable with the use of different active spaces. And well, this is basically the biggest property that I checked beside
Transition
the energy,
dipole.
transition dipole moment, because we wanted to be sure, for instance, that we were still optimizing a bright excited state. A problem that we met sometimes for the optimization of the pi star molecule state of acrolein was that the bright excited state during the optimization was somehow mixing with some lower energy excitations. So of course we were looking at this, and we had to stop, for instance, the optimization, and we had to start from another minimum. So from another point, in order to avoid this problem in the description of the nature of the excited state. So, but I can say that generally properties such as transition dipole moment are quite stable. Properties as the molecular dipole, so the permanent dipole of the molecules, are also quite stable with respect to the change in the size of the active space or other computational ingredients.
Okay, well, thank you very much for these explanations.
Okay, thank you, Professor Groenenboom. Then we move over to this side of the table, and I'd ask Dr. Brox to continue the opposition.
Waarde promovendus, let me also start by congratulating you with your thesis. I enjoyed reading it very much. Naturally, I have some questions. The first question I would like to start with is a very basic one. In the first part of your thesis, you give a very nice overview of all the theoretical methods you use. And you indicate how, in principle, one should calculate excitation energies. Namely, if, for instance, you go to page 28, you say, okay, one has to look at the optical response function, and then look at the poles in the optical response function, and those are the excitation energies. And you calculate the optical response function by means of a linear response. Now, if you go to your later chapters, 5 and 6, where you do linear response, you seem to argue that linear response is not everything, that it doesn't give you the whole story. For instance, if you go to page 146, which is one of the figures in your last chapter, Um, I see there a graph, and the not the last point, but the point before is the linear response result, and you don't seem to be happy with it. It seems to be needing some extra correction. So my question is, why do you need an extra correction if linear response should give you the complete answer?
Um, okay, my highly learned opponent, thank you for your question and comments. So looking at the plot in page 146, what I want to say is that in the use of a polarizable environment, we can model the interactions in two different ways that recover different physical effects. So when we match time dependent with, when we embed time dependent DFT with a polarizable environment, we can induce the response of the environment following a linear response approach and an approach that is state specific. And doing this, we can see that the effects that are included in the calculation are two different parts of the total interaction of the environment with the system that cannot be recovered simultaneously. So,
Well, I understand that aspect, but if you go back to your original page 28, I mean, if I look at all the equations starting with 2.41, for instance,
yes,
that seems to be exact. I cannot argue with that, and that seems to be linear response only.
yes. Okay, so with the linear response, anyway, we would not recover a part that is recovered in the state-specific approach, because we would need to account for a correction of this linear response, which involves the minimization of the energy of the environment with respect to the difference in the densities of the grounded and the excited state. So we actually, in linear response, we actually miss a part of the coupling between the environment and our system. In this equation, I'm thinking and describing an isolated system, while in the case of chapter 5 and 6, I'm dealing with a problem of a nonlinear Hamiltonian, where the solution of the linear response method differs from a state-specific solution. So this is why I'm recovering different effects.
Okay, I'm not quite sure whether I totally agree with you, because a linear response can be done on isolated systems or on extended systems. The equations stay the same, and you can do TDDFT in a solid state environment, and the procedure is more or
Yes,
less
but
the same.
what is changing in chapter 5 and 6 is actually how I'm doing, how I'm tailoring the coupling of the quantum part and the environment. So we from a perturbative approach of this kind of problem, it can be derived that a linear response approach leads to an expression of the excitation energy, which is formally different from the one that can be derived from a state-specific approach.
Okay, let me, since we're on the topic, let me try and give you a suggestion for the response of the solvent. You're modeling the response of the solvent in terms of polarizabilities, which are static polarizabilities. Now, would it not be an idea to introduce some dynamics into this response?
Such as, sorry?
Such as, yeah.
Okay. Such as, okay, so a dynamic response, you mean like changing the values of the polarizability with the nature of the excited state? We didn't attempt this.
Well, I'm thinking of something more obvious. If you have a polarizability,
Oh, something like anisotropic polarizability, maybe.
well, not static, but
resonant polarizability with well, sincerely, well, to increase the complexity and the physics in our coupling, we
I mean,
could ask the
to
anisotropic
me,
polarizability.
the obvious thing to think of is to take frequency-dependent polarizability.
Well,
right. That's
I'm thinking about it. Why should I add it? So yes, sincerely, I wouldn't know how to include it in my model at the moment.
okay. We can discuss it afterwards.
Probably, I don't know.
Thank you very much for your
Yeah,
answers.
you're welcome.
Okay, thank you, Dr. Fox. So we'll leave this problem unsolved for the moment, and I'd finally ask Professor Briels to continue the opposition.
Thank you, Mr. Chairman. So that was a nice discussion, and after all these scientific things, I almost feel like I should start with a disclaimer. I'm a polymer physicist, and all these things are intimidating. Anyway, I did try to read it, and I would like to ask a question, which probably is a very stupid question, but you can give a very good answer in that case. I would ask on page 117, where you do the polarizable surroundings and you calculate dipole moments on the solvent molecules. And my question finally is, which charges should I include in equation 5.9? Suppose I have solvent molecules on which I have several charged sites and several polarizable sites. What should I then include on the as an EQ in equation 5.9?
So my highly learned opponent, thank you for your question. What we do in equation 5.9 is literally to collect the electric field generated by all the charges that we have in our system.
Well, I'm actually referring to, should I take permanent charges plus induced charges in all cases, or are there situations where I only should use induced charges? It's a question. I'm not.
By induced charges, you mean dipolar dipole induced dislocation of the charges, or well, what we use in equation 5.9 are static permanent point charges. So we do not. I mean, in equation 5.9, I define E static as a permanent charge distribution around in my environment, and the charge distribution are generated by the solid. So EQ is a vector containing permanent charges.
But if I calculate the dipoles on a particular solvent molecule, then I would say that the permanent charges on that same molecule don't contribute to any additional polarizability. Is that correct? Or
in our approach, we keep the charges fixed, and yes, it is true that do not change when the dipoles are induced on them, but this is done because, as I said in a previous question, the charges are designed in order to take into account that there will be an action of a polarizable field. So bottom line is that I do not change the value of the charges when the polarizable field is added. So they are developed within to take into account this presence anyway.
My problem actually is if I take an isolated solvent molecule and I do this approach, then I should not induce any dipoles in that molecule.
Sorry, if I have an isolated molecule,
Yeah.
sorry, I think.
Thank you very much, Master of the Ceremony. So we'll have to stop this discussion at this moment. Dear candidate, Paranims, would you take your seat in the audience again? And then I adjourn this meeting of the board, doctorate board of the University of Twente for consultation and deliberation by the committee. Stay online, we will be back. I reopen this public meeting of the doctorate board, and I'd like to invite the candidate and his parents to come here to this table. The Committee of Deans of the University of Twente, represented by us, has examined your dissertation and heard your defense. The Committee of Deans has decided, in accordance with Article 7.18 of the Law on Higher Education and Scientific Research, to admit you to the degree of doctor. I request the supervisor to perform the task with which she has been charged.
Thank you. Under the authority assigned to us by law and on behalf of the doctorate board, I grant you, Riccardo Guareschi, the degree of doctor and all the rights that are attached to this degree. As evidence of this, I present you with the diploma signed by the Rector Magnificus, the Secretary of the Graduation Committee, and all the members of the committee, and validated with the seal of the University of Twente. Dear candidate, dear Riccardo, well, it's kind of a moment to congratulate you from the heart for a very nice defense, but especially for how you successfully performed this journey of 4 very, very intense years, okay, which has led to the work of your thesis. Well, I must say that I think we both recall your start 4 years ago, being a bit tough for you and also for me, not knowing very well how to help you out to overcome the first difficulties. I must say that faced with all the many methods you are using the thesis, and now you master, you even further developed. At the beginning, you were a bit overwhelmed. Okay, maybe you even reached a standstill, but now if you look at it, it looks so far back and really very far history if you now look at what you have achieved in these 4 years. And indeed, I must say you were extremely determined to get this, to get over this start and this first moment, and you were also extremely reliable, and I always trust you very much for your work in these years. Okay, and also I must say you worked very, very, very hard. Also, as I said, your determination was quite remarkable. For instance, your third paper, your chapter, was supposed to be a couple of months. We sat down, we said, oh yeah, that's easy, we just do it, and it took 1.5 years. You had all sorts of problems with implementation, multiple runs, lots of problems with very simple molecules. If we look at them, you say, well, why don't you just do the spectrum, as one of the people asked? But actually, there were very, very hard problems, and you didn't give up. Well, I must confess now that I was quite concerned about you finishing your Ph.D. in 4 years, okay? But, okay, well, you must say that, your determination, you really went through this, and in particular, your last chapter, you just did it so quickly, also with the writing and everything, okay? And something also I must prize, in addition to your ability of really absorbed all this knowledge and further elaborate, was the organizational skills. I mean, you were really always very organized, setting very concrete, setting very precise goals, and then going through boom, 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 one after the other. Okay, and I must say also in practical issues, you always had your talks, your poster prepared well ahead of time, differently from some of your current and past collaborators. I'm not gonna give any name, and and also you handled also all the talks and presentation with lots of self-confidence and really with mastering what you had done. And I must say, also seemed always very balanced, with handling work, your sports you like so much, and the private life. This balance also in organization also appears in small things. For example, I've been always very impressed. For 4 years, you woke every morning, cook your lunch, and brought your lunch at work. I just don't possess this type of organization. Okay, I must say that the menu was a bit repetitive. I think you ate for 4 years chicken, rice, and salad, but nevertheless is quite impressive. Okay, and well, I know that now you're going to be looking for a job in industry, and actually, it's quite nice. I think that you want to stay in the Netherlands, which, by the way, means you're going to eat much more rice. Chicken and salad, but except this aspect, I'm sure that whatever company will actually take you will really gain a lot and have a really a very valuable asset. Okay, and so I know that not all the years were easy. As I said, there were up and downs, and maybe you let other people think that everything was always very fun. You have this ability, and also maybe in the first year we also had some clashes, but I mean I think we overcome them very very well, and I really hope that you are as proud as I am of the work and the thesis you have achieved. Okay, and now, well, I stop. I don't want to keep you from your family, and I congratulate you again. I wish you a very serene and successful future, as bright as your PhD. And I would like to congratulate you.
So, Dr. Guareschi, also on behalf of the university, from my side, congratulations with the completion of your work and with this defense today, which we have heard, and we also have here a little book for you with the signatures of all the members of the committee to keep as a memory. It's always great. I have been impressed. I did not have the pleasure to read your book, but I saw many things. And, oh, that's interesting. I would like to know more about. Okay, it's a pleasure to hear that you're planning to stay in the Netherlands. Of course, there's an alternative. You can get used to croquettes and the likes, but maybe you prefer staying with the chicken, salad, and rice. That I could understand. So I wish you all the best for a bright future in this country with your degree and with all the skills that you have achieved. Okay, congratulations. Good. So then I'd like to ask you to take your seat again for the last time. And with this, I close this meeting of the doctorate board. We're going to leave the room led by the master of the ceremony, the young doctor, and the people from the first row here, and then the committee is going to follow, and the rest of the audience, and we're going to take a left for a short photo moment outside.